My name is Jon Huddleston. I'm the Director of the Concrete Industry Management Program at MTSU, and I want to talk to you a little bit today about the program, why it's unique, and some of the technicality in concrete. First of all, concrete is different than overall construction because we're looking specifically at a building material. We're talking about the number 2 most utilized material in the world next to water. And of course, concrete uses water in it. So we have found our industry likes to see that people are well versed in concrete, the chemistry, the understanding, and the material itself. So we'll start out a little bit on the technical side to begin with. We do a lot here at MTSU when it comes to the technical side. We have a lot of students who come in and believe that concrete is just a bag of Quikrete or a bag of Sackcrete from a local big box store, and that's kind of their exposure that they've had. But we look at concrete a lot differently here. And so we've got a lot of different things going on, and we talk about bridge decks and high-rise structures, and that's where our concrete construction is primarily focused, that and utilities and infrastructure. But here we have a Department of Transportation research project going on where we're looking at the shrinkage of concrete. People think about concrete, they think about how hard it is, and surely that stuff cannot shrink, right? Well, the reality is, if we're talking about a 1-foot long piece of concrete, it doesn't shrink much. But when you pour an Amazon fulfillment center or a Facebook data center or a bridge deck, it does shrink back. So many of you have gone across the road and you felt that bump going onto a bridge. That's expansion and contraction that causes that. And so what we're doing here is we're measuring the expansion and contraction of the concrete using a steel ring and a lot of technical sensors, which I won't get into today. So that's just one of our projects. Also, when it comes to concrete, we're in a unique state here. We use a lot of de-icing salts in the winter. So this thing has a lot of wires. It's not hooked up right now, but we're looking at chloride permeability. So chloride being salts, we're looking at how easily those de-icing salts get into a bridge deck and then attack the rebar inside and cause the bridge to break down over time. You've heard a lot in the news about degrading bridges across the country. So here's what we do, a little bit of analysis there in new mix designs and how we can increase the longevity of those bridge decks. So we're looking at chloride permeability, passing electric charge through the concrete, and how easily those salts can attack it is indicated by how easily the current can pass through the concrete. And then here in Tennessee, when students come in, I like to ask them a question. Do you think freeze thaw is a bigger problem in Tennessee or in Milwaukee, Wisconsin? And a lot of them think, oh, Milwaukee, it's cold in the winter, right? The reality is it's a bigger problem in Tennessee because Milwaukee, when they freeze in the winter, they stay frozen. They might thaw out every few weeks or so as the weather changes. But here in Tennessee, it's not unusual for us to see a 45-degree day in January and 20 degrees at night. And that really wreaks havoc on our bridge decks and our infrastructure. So what we're doing here in this chamber, we have a lot of different formulations of concrete, and we're looking at how easily it holds up under freeze-thaw conditions. So over a whole 1-day period, we'll freeze this and thaw it out 6 times. So that equates to 1 week here in Tennessee during the winter. And in Tennessee, it has to withstand 300 revolutions or freeze-thaw cycles, whereas in Wisconsin, they actually only have to withstand about 140 freeze-thaw cycles. So a little bit of difference there. We have a much harsher climate when it comes to concrete, believe it or not. And then right here, of course, what everybody likes to see is, hey, concrete, we hear it's strong. So we like to come over here and we'll put a cylinder in here. This particular concrete is something we've been working on with a bridge deck here in Tennessee towards the Franklin area. And we've been looking at ways to replace cement and keep the strength of concrete. Because the most expensive thing in a concrete mix, which we sell by the cubic yard out of a ready-mix plant, is the cement itself. So we're looking at variation, different types of replacements, green products, coal ash, and things like that we can put in the concrete, still achieve the same strength, the same permeability resistance like we talked about with salt, and then we'll crush it in here and see how strong it is. So I'll run one real quick, and you can see the we'll have to close it for safety purposes here, but it should make a nice strong sound. Right now it's up to 700, 800 PSI, that's pounds per square inch. And the standard on this in Tennessee for a bridge deck is supposed to be a minimum of 6,000 PSI. So anyone that drives a crew cab truck out there, that's about like taking one of your trucks and putting it on 1 square inch of that bridge deck. So far we're up to 1,500 PSI, we're getting there. Still got a little ways to go. does take a couple of minutes. Not the fastest thing, but certainly a strong product. And so at 6,000 PSI, that's a bridge deck. If we wanted to do columns in a high-rise building like you would see in downtown Nashville, that may be along the lines of 8,000 to 12,000 PSI, depending on the structural load. The footing for those high-rise buildings can be around 20,000 PSI, because you got to think about all the weight that it has to support above it. And then to get that, that's not always the easiest thing. It's not just going to be regular cement and sand and rock. We're also going to utilize chemical admixtures to increase this, or accelerate the set time, to increase the strength, to make sure that all the particles of cement, a lot of people don't understand that not all the particles of cement and concrete hydrate. So that's why concrete continues to get stronger over time. If you go to Rome, all the concrete that you see there and the mortar and the aqueducts is continuing to get strong thousands of years later because of unhydrated cement particles continuing to hydrate and continuing to add strength. So far we're at 4,500 PSI, so we're just about to the specification required by TDOT. This particular mix, it broke a little weak. So that was 4,811 PSI, so it's got a little further to go. It's not quite at its full term strength. We like to take that at 28 days. But then we'll look at it, we'll pull the cylinder out of the machine and we'll see what type of break we got. And this is not the most ideal. We want to kind of see the whole thing obliterated or cracks all the way through the top, and then it comes into a cone form at the bottom. But this right here is a silica fume replacement, so it should actually at 28 days be stronger than the concrete required. But this wasn't the best break. It probably is in reality a little bit stronger. We probably had a high spot on this cylinder that caused that. There's a lot of other technical things that we do here in concrete industry management. This is just a small sampling of all the capabilities we have. We like to go out with students. We are unique in that we take you out to job sites. We give you as much exposure as possible. Give you an idea, we teach a decorative concrete class, and it is a completely hands-on class, application, stamping, vertical wall carving, staining, sealing, all kinds of things in that niche of the market. In addition to that, we have a cement class where we go through a little bit of chemistry. It always scares students a little bit, but everybody seems to make it through just fine. And then at the end, we actually go to one of the 2 cement plants here in Tennessee and give them full exposure to the entire process and the understanding. Stop this.